The binomial distribution. Let's get started. Let's say that you have a die and you're going to roll it 3 times, and the die has 2 green faces and 4 blue faces. So I have a tree diagram here representing the situation. So the probability of getting a green in the first roll is going to be 2 out of 6, and the probability of getting blue in the first roll is going to be 4 out of 6. And carry on with our tree diagram as we see here. So getting green, then green, then green would be those branches, green, then blue, and so on and so forth. Well, let's talk about that, like mapping out each individual outcome. So like I said, that first one, that would be green, green, green. And then the next one, that's green, green, blue, and so on. And now we have all 8 possible outcomes for rolling our special color-coded die here. Now, let's talk about the probability of each of these events happening. So green, 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 well, that's going to be 2, 6 times 2, 6, so 2, 6 to the third power. Green, green, blue would be 2, 6 times 2, 6 times 4, 6. Then green, blue, green is 2, 6 times 4, 6 times 2, 6. And so on and so forth until we have these totals here. Now, you'll notice that I have the blue check mark next to these expressions because these expressions are all the same. So I have 3 of those, and then with the green star here, those expressions are all the same. And recall that if we take the probability of all of the events in our sample space and we were to find their sum, we would get 1. So what I have now is that 2, 6 to the third power plus 3 times 2, 6 to the second power times 4, 6 plus 3 times 2, 6 to the first power times 4, 6 squared, blah, blah, blah. That's all equal to 1. Now, this is what's known as a binomial expansion. These coefficients here, the 1 and then the 3 and the 3 and then a 1, these are part of the binomial expansion. Now, you may not have heard of something called Pascal's triangle, but let's talk about Pascal's triangle. Actually, let's talk about a binomial expansion. If I were to have something like x plus y to the first power, well, that's going to be equal to x plus y. If I had x plus y squared, that would be equal to x squared plus 2xy plus y squared. I'm going to do a few more. So with x plus y cubed, remember that would be x plus y times x plus y times x plus y. And so when you expand it, you're going to get x cubed plus 3x squared y plus 3xy squared plus y cubed. Similarly, for x plus y to the fourth, write that out 4 times and multiply it all out. Bear with me here while I explain this meaning. What I want you to look at is the coefficients in all of these expressions. So 1, 1, 1, 2, 1, 1, and so on. Now, if I were to take those coefficients and get rid of all of the variables, then I would have these numbers, 1, 1, 2, 1, etc. Now, one thing I did not include was if I had the binomial x plus y to the power of 0, which would be equal to 1. These numbers here are Pascal's triangle. You'll notice you got 1s all down the sides. So the way that you would get the 2 is you can add the 2 numbers above it. And then the 1 plus the 2 gives you the 3. The 1 to 2 plus the 1 gives you the 3. 1 plus 3 gives you 4. 3 plus 3 gives you 6. 3 plus 1 gives you 4. But we can easily write down the next row of Pascal's triangle, and that would be 1, 5. So this is known as a binomial expansion because we've just taken this binomial x plus y and raised it to different powers. And then these coefficients are what we find interesting. So these are the same coefficients, 1, 3, 3, 1, are the same coefficients that we saw in row 3 of Pascal's triangle. Well, there's another way that you can get these coefficients. You can use combinations. Remember when we did permutations and combinations, you use combinations. So I also want to point out, let me back up to this step over here, that the variables on the x are decreasing. So x squared, x to the first, and then x to the 0. X cubed, x squared, x to the first, x to the 0. Here, x to the fourth, x cubed, x squared, x to the first, x to the 0. And then your y variables are increasing. So you have y to the 0, y to the first, y squared, y cubed, and so on. And then one more pattern, which is that the sum of the exponents is going to add up to whatever you're raising your binomial to. So 1 plus 3, because this would have an exponent of a 1 here on that y. So 3 plus 1 is 4. 2 plus 2 is 4. 1 plus 3 is 4. 4 plus 0 is 4, right? Because there would be a 1 there at that 1. And same thing back here. So 1 plus 2 is 3. 2 plus 1 is 3. And 3 plus 0 is 3. And then that power there was 3. So when we see this in what's called a binomial expansion, For binomial probability, we'll talk about how you recognize that in just a second. We're going to have the coefficient, which is found by using combinations of n choose k, and then you're going to have p. We'll talk about that in a second, what p is. P to the power of k, and then q to the power of n minus k. And notice that if you do n minus k plus k, you're going to get n, right? N minus k plus k, that's going to give you n, all right? Hold on to that. How do you know if it's a binomial probability situation? We have an acronym, and the acronym is BIPS. So you need to remember this. First of all, the situation is binary, that you have success or failure. So it's happening or it's not happening. There's nothing in between. All of your trials in your experiment are independent. So it doesn't matter what happened in the first trial. The second trial is independent of what happened in the first trial. The number of trials is the number of trials is fixed, meaning that you're going to stop after a certain number of trials. And then the probability is the same throughout. So we're related to the independent, that the probability is not changing as you go through the experiment. So a binomial probability distribution, and this is how we're going to denote it, it's going to be the probability that x is equal to k. It's going to be this combination of nck times p to the power of k, and then I now have 1 minus p to the n minus k. I'll get to that in a second. P is the probability of success. 1 minus p is the probability of failure. So this comes back to the idea of it being a binary situation. It's success or failure. So probability of success, and now instead of, I did Q in the other slide, but now I'm calling it 1 minus P, that's your probability of failure. N is going to be your number of trials. K is your number of successes, and N minus K is your number of failures. For expected value would be the number of times you expect it to happen. We're going to use the notation E of X, so a capital E for expected value and a capital X. Make sure you're following the case here. Capitals and lowercase have different meanings. Equals mu sub X, which also equals to N times P. So the mu sub X is really just another way of representing E of X. Okay, so this is the Greek letter mu, is spelled mu. So it's the Greek letter mu with a subscript of X, a capital X. And the way that you calculate it is just going to be N times P. So N is your number of trials times the probability of success. And that's going to be your expected value. It's pretty straightforward. Now, the notation that you'll sometimes see written for binomial distribution or binomial probability distribution is a capital B and then the parentheses N comma P. So if you had something like B and then 7 comma 1/2, that would mean there are 7 trials and the probability of success would be 1/2, and then the B indicates it's a binomial probability distribution. So if we go back to the opening problem, we had 1 fair die, we tossed it 3 times, we have 2 green faces and 2 blue faces. The probability of getting exactly 2 green faces. So we're going to have N is 3, that's your number of trials. Your probability of success, K, is going to be 2 because you want exactly 2 green faces. So N minus K, of course, is going to be 1. The probability of success, since we want 2 green faces, that's going to be 2 out of 6 because there are only 2 green faces. And the probability of failure, or 1 minus P, is going to be 4 out of 6. So when we put that all together in this formula here, we're going to have 3C2 times 2/6 to the power of 2 times 4/6 to the power of 1. Okay, a few things I want you to notice here. The exponents, the 2 and the 1, that's going to add up to n, and n is, of course, going to be that first number for your combination. The 2/6 and the 4/6, that adds up to 1, because the probability of success plus the probability of failure is going to be equal to 1. So from your calculator, you can find 3C2, the combination of 3 items, choosing 2 at a time, which is going to turn out to just to be 3, and then 2/6 squared times 4/6 to the first power, and that's going to work out to be 0.2 repeating, which is 2/9. So there's a 2/9 probability of getting exactly 2 green faces when you toss a die 3 times. Number 1, Kyle guesses at all 10 questions on his multiple choice test. Each question has 4 choices. Find the probability he gets 6 correct answers. So let's write down what we know. Our number of trials is 10 because there's 10 questions. The probability of success, since he's guessing, is going to be 1 out of 4 because each question has 4 choices. So then his probability of failure is going to be 3 out of 4. And then the number of successes that we want is 6. The probability that he gets 6 correct answers. Pause the video and put all that together with the formula. So what we have is a probability that x is equal to 6. That will be our formal notation. It's going to be, now here's something different. I'm going to write 10 And then a 6, like this is the same thing as saying 10C6. Sometimes you might even see it written as like a C, open parenthesis, 10 comma 6. You might see it like that as a combination. Then our probability of success, 1/4 to the power of 6, and then 3/4. We have to raise that to the power, remember the exponent here, and the exponent on the probability of success has to add up to 10. So if this is 6, then our probability of failure, we're going to raise that to the 4th power. So this number is always going to be the same as this number, and then the exponents, of course, have to add up to n. Okay? And then when you go to your calculator and you calculate that, you're going to get about 0.0162, which is 1.62%. Number 2, 8 out of every 10 persons who contract a certain viral infection can recover. If a group of 7 people became infected, what's the probability that at least 6 people will recover from the infection? So this is kind of unique in that we have the at least 6 people. So let's write down what we know. For part A, our number of trials is 7. The probability of success, so that's going to be the probability that you can recover. Well, 8 out of 10 people can recover, so the probability of success is 0.8, which means the probability of failure is 0.2. All right, now when we say at least 6 out of 7, that means 6 or 7. Okay, now if we had a total of 17 people, it would be 6 or 7 or 8 or 9 or 10, all the way up to 17. But we have a total of 7 people and we want at least 6, so that means 6 or 7. So we're going to have to do 2 separate things and add them together. So we have 7 choose 6. Notice my notation. You can definitely use the 7C6 if you prefer that notation. 0.8 to the power of 6, 0.2 to the power of 1, or means to add 7 choose 7, 0.8 to the 7th power, and 0.2 to the power of 0. Of course, 0.2 to the power of 0, that's just equal to 1, so you don't have to write that part. And when you go to your calculator and calculate this, you're going to get it to be approximately 0.5767, which of course is 57.67%. Now, for the expected value, remember expected value was E of x or mu sub x. That's going to be just your number of trials. Now this time it's 30 because it says how many people in a group of 30 are expected to recover. 30, and then the probability of recover is 0.8. So that's going to give you 24, which should make sense, right? That if you're saying, well, there's 30 people, and if you have an 80% chance of recovering, then 80% of 30 people is 24 people. So 24 of 30 people are expected to recover. Now, you can do binomial probability distribution in your calculator. You want to go to second distr menu in your calculator, and then you're going to search for option A, binom PDF, and then you put your number of trials, comma, your probability, comma, R, the number of successes that you want. For a cumulative binomial probability, we're going to do that in just a second, you would want to use the binom CDF with number of trials P and R. So I've opened my calculator app. This is not the exact same type of calculator, that's the 84, but if you do second VARs, that's the distribution menu. And you want to go all the way toward the bottom there and find binom PDF and binom CDF. So if I choose binom PDF, and it says for n, yours is going to look different on the 84, but for maybe example number 1, with Kyle guessing on the multiple choice, I could have said 10, comma, 0.25, because it's a 1 out of 4 chances of guessing, and then we want to be successful 6 times, and I press enter, and then I get the value. Okay, number 3, same scenario as number 2. 8 out of every 10 persons who contract a certain viral infection can recover if a group of 7 people became infected. What's the probability that less than 3 people will recover from the infection? So here's where it gets a little tricky with the English language. The probability that x is less than 3, well, since we're just talking about people, it's got to be whole numbers, right? It's going to be the probability of x being greater than or equal to 2, or in other words, the probability that x is equal to 0, plus the probability that x is equal to 1, plus the probability that x is equal to 2. So the probability that nobody recovers, the probability that only one person recovers, and the probability that 2 people recover. So you want to do these also individually, like so. 7 choose 0, 0.8 to the 0, 0.2 to the 7th, plus so on and so forth. You can also do the binom CDF. Now CDF, this is always when you want to do at most. So 2 all the way back down to 0. If you're not comfortable with the calculator notation, I would recommend that you do it individually like that. But the important thing is that the CDF is only for at most. So that many successes or less than that. You would not use binom CDF for something like 6 or 7 because that's doing 6 or more. And if you did the binom CDF with the 6 at the end, it would take you 6 all the way down to 0. And if you did it with 7, it would take you 7 all the way down to 0. So be very careful with that. You can actually see right here, I would do this with 2 separate binom PDF commands to check your work. Last example, 18% of items produced from an assembly line are defective. 10 items have been selected. Find the probability that of those selected, at least 2 are defective. So here's another at least situation. But here's the thing, if you're saying at least 2 and you want 10, then you're talking about 2 or 3 or 4 or etc., all the way up to 10. That's going to be very tedious to calculate all of those individually and add them up. And if you can't do really binom CDF of 10 down below because it'll take you all the way down to 0. So the most efficient way to handle this is actually to turn the at least to use a complement. So the probability of having at least 2, so greater than or equal to 2, is going to be 1 minus the probability that x is less than or equal to 1. That's going to be your most efficient way to handle it. So 1 minus the probability that 0 of them are defective plus the probability that 1 is defective. So then it would be 1 minus, and then you can do 10C0, 0.18 to the power of 0, 0.82 to the power of 10, plus 10C1, 0.18 to the power of 1, 0.82 to the power of 9. And when you calculate that, you're going to get about 0.5608 or 56.08%. And you can see this is where you can use the binom CDF command, but also with the complement. Again, if the calculator command confuses you, just do it individually. The end.